Hello everybody and welcome to a new episode of the Technical Tea Breaks. My name is Stefania Marcotti and I'm a postdoc in the Stramer Lab at King's College London. My main research interest is in bioimage analysis, and in the next 15 minutes or so I'm going to give you an introduction to image analysis in Fiji. So get your tea or coffee ready and let's get started. The learning objectives for today are the following. First of all, we're going to find out what Fiji is, and we'll see some basic theoretical principles on what makes an image, an image. We will then move to Fiji itself and perform some basic operations. How to open an image, how to separate channels, visualize histograms, and how to adjust brightness and contrast. Okay, so what is Fiji? Fiji is an image processing software based on the Java scripting language. Specifically, it's a distribution of ImageJ, which you might have heard of before. Fiji has some specific plugins that are there to facilitate scientific image analysis, and that is the reason why we're focusing on it in this technical tea break. Okay, so what does make an image? Here we see one of the sample data that are built in Fiji. It is a fluorescence microscopy image showing some endothelial cells stained for nuclei, tubulin and F-actin. Do not worry if you're not familiar with what they are in biological terms. We need only to focus on the fact that there are three structures that were stained and imaged on the same sample. The signal from each structure was saved in a separate channel of the image. We can think of a channel as a container where the information for that particular structure and signal is stored. We can assign a color to each channel for visualization purposes, especially if we want to display more than one channel in the same image. But this is only a convention, as each channel is built in exactly the same way. We're going to focus on the first channel, and in this image in particular, and we'll explore it further. If we zoom onto a small region of the first channel, the container for actin, we can see that the image is discretized in small squares that we call pixels, which are assigned a numerical value. This numerical value depends on the fluorescence intensity of that structure at the moment in which the image was acquired. Pixels containing no signal, so background pixels, like the ones here, will have low value, let's say 0. Very bright pixels will have, for example, had a very strong fluorescence intensity, are assigned a high value, so let's say 1. We can build a graph that's called a histogram by counting how many pixels carry each value between 0 black and 1 white. For this image, we see a peak around 0 over here. You can see a very tall bar, meaning a very high count. And this relates to the pixels that are in the background, which are a few in this image. On the other side, we have a smaller peak for pixels which have values equal to 1. So fluorescence intensity there was as bright as it could have been. These are often, in this image, localized around the cell edge, as you can see here, where like a brighter edge can be found. Finally, we have a number of pixels that are in between 0 and 1, which correlate to the other structures in the image, so in this case, actin stress fibers. So it turns out that what makes an image are numbers. Who would have thought? But how many numbers do we actually need? So I told you that to build a histogram, we count the pixel for each intensity between 0 and 1. How many values there are between 0 and 1 depends on what is called the image depth. In the example on the left, we have a low number of values between 0 and 1, and we increase it progressively as we move from left to right. I am sure you can appreciate that the more values we allow between 0 and 1, the more we can distinguish between subtle difference in intensity. As a convention, images contain a number of values which is equal to 2 to the power of something. This has to do with computers, bits and bytes, but we don't have to go into too much detail in that direction. I will paste more in the resources at the end if you're curious to know more about it. What is important to know is that the most common formats you'll find in scientific images are 8, 16, and 32-bit, with increasing number of values between black and white. In fact, for 8-bit, for example, we have a number of values which is equal to 2 to the power of 8, so 256 values. So values going from 0 to 255. The same goes for 16. Of course, 2 to the power 16 is a higher number, and 2 to the power 32 is even higher. Remember that the deeper the image, the more information can be stored inside it. We have more shades of intensity available, so there's more information that can fit in there. However, also the size of the file will increase. It's a matter of balance on how much detail we need and how much space we have to store that detail. The final theoretical concept we're going to cover is resolution. You will remember that we mentioned pixels just a couple of minutes back as the building blocks of the image. The number of pixels available for a given length decides the image resolution. Here from left to right, you see the image resolution decreasing. For the same length in the image, we have less and less pixels, or we could think of as we have bigger and bigger pixels as the image resolution decreases. A unit to measure resolution, which you might have come across before, a DPI, or dots per inch. This refers specifically to an image being displayed on screen or printed, and refers to the number of pixels that are available in 1 inch. And by the way, this is 1 inch in the top right, in case you were wondering. Okay, enough theory. Let's have a look at Fiji and test some of what we've learned so far. Okay, so this is how Fiji looks. It's a taskbar with a few menus and buttons. You can see here. Let's first learn how to open an image. This is pretty straightforward. If we go in the menu up here and we click on File, Open, we can then select a file from our machine. For the example we're going to look at, we're going to open a sample image. To do so, we go into File again, but this time we click to Open Samples, and we select Fluorescent Cells. The list of sample images already available in Fiji is very long, and if you're curious, I'll paste more resources at the end. Rings a bell? We've seen this image before. This is the image of the endothelial cells. The color for display are not exactly the same, as I had magenta instead of red before, but remember that these are only there for visualization, so it doesn't really matter which color is assigned to which channel. Keep in mind, though, that some conventions might apply in some disciplines, so it might be worth asking other researchers around you on which color they would display each of these structures. Let's now divide the image into its 3 constitutive channels, or containers, as you remember. And to do so, we go again into top menu, and then we go into Image, Color, and Split Channels. Ta-da! Here they are. Channel 1 for actin in red, Channel 2 for tubulin in green, and Channel 3 for nuclei in blue. We will explore the first channel in a bit more depth, so I go on and close the green and the blue image. Here is our Channel 1. The first thing we're going to do is to change its display color to gray. To do so, we go again into the top menu and go into Image, Lookup Tables, and then Gray. This is the menu we can use to change any channel display color. So we could also change it before to magenta, as I did it earlier, or any other combination if we have more than one channel. But for now, we decided we wanted gray, so Lookup Tables, Gray. And here it is, our Channel 1 in gray. Let's zoom in and look at the pixels. We can do so by clicking on the little magnifying glass that you can find here in the taskbar. We can appreciate some black backgrounds, so some black pixels, and a range of intensity between brighter and darker structures. The little map here on the top left corner gives us an indication on where we are on the image, and it's quite useful if we zoom in too much and we got a bit lost. Let's zoom out again then. Okay, let's zoom out again then and check how to plot a histogram for this image. We can click on Analyze in the top menu and Histogram, as easy as that. And here it is. Remember, we've seen this before. We count pixels for each intensities with a lot of them in the background and a few very bright structures. We also have some further information here below the histogram that tell us something related to, for example, pixel count, minimum, maximum, mean, and standard deviation of the intensity. The image we're looking for is 8-bit, as we can see here just above the display. So what we expect is between 0 and 1, 256 values, so 2 to the power of 8. In fact, if we look at the color bar over here, we have 0, black, and 255 assigned to white. Okay, last concept for today's tea break is related to adjusting brightness and contrast on an image. We're going to test this on a copy of our image, which we can obtain by clicking on Image, Duplicate. So again, in the top menu here, Image, and then Duplicate. This duplication of images is very, very handy if we want to test some operations but we're not sure of the results. It allows us to play around with things on a copy of the image without affecting our original file and raw data. So now we have two copies of the image. The one on the left is our original data with the histogram plotted, and the one on the right is a copy that we're going to use to run some tests with adjusting brightness and contrast. To do so, we go again into our menu on the top and go Adjust Brightness and Contrast. This little menu on the right has opened up. Let's make sure that we have the copy of the image selected, so the one on the right, and we can play around with the slide bars here. We see the histogram plotted, again, similarly to what we had for the image on the left, and we see a diagonal line. This diagonal line is indicating how we are affecting the value of the histogram. When we adjust brightness and contrast, what we are effectively doing is to chop part of the values, squeezing or expanding the histogram towards lighter or darker values. Let's select some values here and click Apply on the brightness and contrast menu and see this in action. Oh, we get a warning here. Why? Adjusting brightness and contrast can be useful for visualization purposes because we can bring up some of the structures. But remember, if we change the histogram, we are changing the numbers that constitute our image, and therefore we are changing our image itself. If we are interested in quantifying the fluorescence intensity, it means we are interested in the numbers that each pixel carried, so we don't want to change that in this way. Let's demonstrate this by plotting the histogram of the new image and comparing it with the original version. The histogram for the image on the right looks indeed differently to the one on the left, and this is because when we adjusted brightness and contrast, we affected the image histogram. So take-home message here is, if you change the value of the image by modifying the histogram, for example, and brightness and contrast adjustment is the easiest way to do so, then what you're doing is effectively changing the numbers that constituted the image, and you're discarding information that might be useful. So be wary. If you want to quantify an image, don't change its histogram. Okay, enough for today. We learned about the software Fiji, and we went through some basic theoretical concepts on how an image is formed. We also learned how to perform some basic operation in Fiji. I hope this introduction will give you the confidence to further explore the software and, of course, the beautiful world of bioimage analysis. Here I copied some links for further readings and more in-depth training resources. I hope you will find them useful. Bye for now. This is the end of today's technical tea break. See you next time.